We're going to talk about what's called differential voltage analysis. And this is a very, very important tool that you can use to understand why cells are failing and also to reverse engineer other people's cells. So I just want to remind you that lithium-ion cells have two intercalation electrodes. Both of them have voltage versus capacity curves that show features when you measure versus lithium. So therefore, when you take the difference between the positive in black and the negative in red to get the full cell voltage curve, the full cell voltage curve shape will depend on the N to P ratio. For example, if you have a lot more negative, this bump will shift to the right, and the feature corresponding in the full cell, you can just barely see it here, will shift to the right. And if you have more SEI growth on the negative side, the whole negative curve will shift to the right, and all these corresponding features in the full cell curve will shift to the right. So the details of the full cell voltage curve can be used to learn about the nature of the positive and the negative electrode. So like I say, the relative electrode slippage, the N to P ratio, and active material loss affect the full cell voltage curve. So let's have a look at this. So you have a positive and a negative. The negative can shift to the right as SEI growth occurs. That will reduce the capacity of the cell to operate in this range, shaded in yellow. The positive will be empty, and then the negative will be empty over here at the left side. If you had more negative electrode in the cell, this is a larger N to P ratio, well, then and a smaller relative shift between the electrodes, then the full cell capacity would be larger. And the full cell voltage curve will look different. So here's a really nice example. These are some data that we collected long ago on lithium manganese oxide spinel graphite 18650 cells. These were power cells, very low capacity but high power. And we ran them at 50 degrees C at a C rate of only C over 14. And if you look at the differential capacity of these cells versus voltage, just over 2, 5, 10, 15 cycles, it changes dramatically. So you ask, why is the differential capacity changing with cycle number? Is there a loss of active material? Positive active material loss, negative active material loss? Is there relative electrode slippage? Does the negative move to the right relative to the positive? What's going on? And your goal as a battery person is to fix the problem so that the cell does not degrade. So if you can figure out what's wrong, you have a chance to fix it. So in this particular paper that my daughter Hannah wrote, we developed a user-friendly differential voltage analysis freeware to analyze degradation mechanisms in lithium-ion cells. And I'm going to talk about DVDQ analysis software today. And you'll have a homework where you get to use our freeware to help understand what's happening in lithium-ion cells as they cycle. So why is DVDQ useful? Well, features are more prominent than in the simple voltage curves. If you look at this voltage curve, voltage versus capacity, you can see there's some features. But if you plot the rate of change of voltage with charge versus capacity, the features are much more easily observed. And it's much easier to fit and obtain information about electrode behavior if you try to fit dVdq. So you have a lot of choices of derivatives you can take and things you can plot that derivative against. So we use dVdq versus q. Why don't we use dq/dv versus v? Or dq/dv versus q? Or dVdq versus v? Right? Well, there's a very nice paper by Konkura of Hitachi that explains why you pick dVdq versus q. And I'll go through that argument here. The voltage of a cell as a function of capacity is equal to the voltage of the positive electrode at the same cell capacity minus the voltage of the negative electrode at the same cell capacity. So this is obvious. So if you differentiate this equation, you get dVdq for the full cell equals dVdq of the positive electrode minus dVdq of the negative electrode. And these are things that you can easily measure in half cells because the charge in the full cell is equal to the specific capacity of the positive electrode times the mass of the positive electrode, and the same for the negative. So this quantity V as a function of QP, this is the positive electrode reference curve. And V as a function of Qn, that's a negative electrode reference curve. So these quantities are easily obtained by making half cells. And then you can take the half cell reference curves and take the difference between them to get the full cell voltage curve. So this is how it works. You have a positive electrode and you have a negative electrode. And each of those can be differentiated to give dVdq. So the black curve is dVdq of the negative, and the blue curve is dVdq of the positive. And then you take the difference between those. You want dVdq for the full cell, so you take dV by dq of the positive, and you realize that Q of the positive is the mass of the positive times the specific capacity. So if you have the reference curve data, voltage versus specific capacity, and you know the mass of the positive electrode in your cell, then you're set. If you don't know the mass of the positive electrode in the cell, you can figure it out by fitting to the experimental data to get the mass of the positive electrode in the cell. The same for the negative side. So this black that you see here is actually the negative of dV by dQ for the negative side, because the voltage goes down with capacity. So we just plotted the negative here just to make it clear what's going on. And then you take the difference between the blue and dVdq for the negative to get the red, the full cell curve. So you would add the black and the blue together to get the red.
Hey Jeff, would
Yeah.
we get the same thing in the full cell? The blue, the red curve?
Yeah, we're going to see that in just a second.
Okay, all right.
So my daughter Hannah wrote the first version of the dVdq analysis software back in 2012, and then Asher Wright upgraded it and made it really quite good later on. And I'm going to go through it and give you an example of how to use it. We'll use it, show you how to use it, and so forth. So this slide is just going to walk through the features of the program. First, you load up specific capacity versus voltage for the positive reference electrode, so that you have half cell data that you load into the program. And then you load specific capacity voltage for the negative electrode. So you have some half cell voltage capacity data that you collected in a half cell, and you load that in. Then the program will take the measured dVdq versus Q, that's the gray curve that you can see here, and the calculated full cell data, which is the green curve you can see here. The reference curves are also displayed, blue for the positive and red for the negative. And the measured voltage curve of the full cell is also displayed up above. And the fitting range, you can use fitting to fit the various parameters in the program. The fitting range is displayed by this gold bar down at the bottom. What are you allowed to vary? There's 4 things. You have the negative electrode active mass, the positive electrode active mass, the negative electrode slippage. What does that mean? That means where do you position the negative electrode starting point in this calculation, and the positive electrode slippage, which means where do you position the positive electrode in this calculation. So there's these 4 things that you can manually adjust, and when you get close, you can automatically fit. If you have a lot of cycles, maybe you have 1,000 cycles, and you want to fit cycle 2, you can fit cycle 2. And then you can just scroll down and fit some other cycle. So it loads all the cycles in at once. It's quite convenient. Like I say, it has fitting capabilities, and it's quite nice. So you can also do things like, if you press this edit button, we'll do this in a minute, and I'm showing this in the PowerPoint because you'll have to do this on your homework. So you'll have a record of what to do in this PowerPoint. My phone is ringing, but I'm not answering it. It's the lab phone, so it's a pain. I can't shut it off. Okay, and then there's an export button down here in the bottom. Oh yeah, so I forgot to say. If you push the edit button, you can create this graph, which is a nice graph. It shows the full cell voltage curve in black and the positive and negative electrodes of the cell, of what's in the full cell, what they're actually doing, you know, how they're shifted relative to one another, and so forth. And our lab convention is to say the capacity equals 0 when the full cell is discharged, as in this graph. So you look at the capacity axis and you wonder, where's the 0 here? Where the black curve reaches the end of discharge, that's 0. And then if you push the export button, you get a spreadsheet of values. So you get, for the full cell, the measured capacity and the measured voltage. And you get the negative electrode, the capacity and the voltage. And you get the positive, the capacity and the voltage. So you can make a nice graph, you know, with better axes and proper labels, better than that. Okay, so I'm going to demonstrate the software now. And we're going to use some data for a Chinese artificial graphite and NMC 111, where the cells are cycled at C over 20. And I have reference curves created for the same graphite versus lithium in a half cell, and the same positive versus lithium in a half cell. So I'm going to leave this PowerPoint and open up the software, and then we'll load the reference curves and so forth. Okay, so let me unshare this and try to share the software. Okay, you should see the software. Is it true?
Yep, it's true.
Okay, good. So now we're going to load up data. So we go File, Load. Now you can load all data at once, but I'm going to just load them one at a time. So we'll start with the negative reference electrode. So it's looking for me to find that somewhere. And I have it in this folder. So I go down, and I'm going to work on charge data. So we have reference data collected for charge and for discharge. So I'm going to pick this charge, and we load that in.
Sorry, Jeff. I don't know. I see only JD on the screen. I don't see any computer screen. But maybe I'm the only one.
How many people see a computer screen?
I can see the DVDQ program.
Yeah, same.
Okay, is anyone taking the class for credit unable to see the DVDQ program? Okay, Ron, you're in trouble. Can't help you.
Okay.
You might want to just leave and come back. Okay, so then we load the positive reference data, and we find the positive. So we're going to take this on charge also. And we load that. There it is. And now we have to load the cycling data. So the measured data we load, it's up at the top. And this is the 3-column full cell VTI. And we load that. Yeah, so it asks you how are you loading your data. Okay, so we're adding it as in the columns, voltages first, then time, then current. So we load that. Okay, so here we are. Up in this box in the right, we have the full cell voltage curve in black. Oh yeah, this is for the formation cycle. I was wondering why the capacity is so darn small. It's because we're on cycle 0, which is the formation cycle. So I'm going to go to cycle 1. There we go. So now we have one of our typical lab pouch cells, about 220 milliamp hours, and you can see the voltage curve of the full cell in black. The measured DVDQ is in gray here, where my mouse is. It may or may not be gray. To my eyes, it looks like gray. Okay. And then the calculated DVDQ, where my mouse is, there's a color that looks like red to me. It may or may not be red. I hope it's red. Anyway, it does not match the measured DVDQ. And it's because we have not adjusted the masses of the positive and negative electrodes or their slippages to make any sense at the moment. So we're going to go and make some adjustments here to improve this. Okay, so we have slider bars that allow us to adjust things. So I'm adjusting the negative mass. I'm making it a little smaller. And why am I doing that? See this feature in the measured DVDQ? That's going to come from the negative electrode. Okay, this is where you have pure stage 2 in the graphite. The voltage drops down and you get a little bump in DVDQ. Okay, so I want that to line up. So I'm going to adjust the negative mass. So now that thing is lined up roughly with that thing. But we're still way off. And that's because the positive mass is really wrong. There we go. We start to increase the positive mass. And now we're pretty close. We can readjust the negative mass a little bit more. There we go. Okay. So the fit's pretty decent, right? Okay, somebody comment. Is the fit pretty decent?
Yep.
Okay, so if you did not know the masses of the electrodes in your cell, the active masses, now you do. You can just read them off these boxes. 0.754 grams for the negative, 1.5 grams for the positive. And this fit is okay, and you can make it better by using the automated fitting. We'll do that in a minute. I just want to show you one other thing. So you should make sure that not only does dVdq versus Q fit well, you can plot dQdV versus V and make sure that it's fine. And you can zoom. Oops, shit. You can zoom. And you can see that the measured and calculated differential capacity versus voltage match up pretty well too. So one thing that's really interesting is if you end up getting a lot of impedance growth in cells, the measured and calculated dQdV versus voltage may not match. They may be shifted by a fixed amount. When you plot things versus voltage, impedance growth causes a shift, the IR drop in cells. We've talked about that in the EIS section. But if you plot dVdq versus Q, the voltage curve just shifts down by a certain amount due to the increased internal resistance. It doesn't change dVdq versus Q at all. So fitting dVdq versus Q is impedance growth independent to first order, which is a good thing. All right, so we haven't adjusted slippages at all. So I'll just show you the slippage just allows you to slide things sideways, right? And I move the negative just slightly. And we can explore what happens if we move the positive around. You know, it changes slightly as well. And then in the end, you say, fine, I'm a human, I'm not as good as a computer, so we're going to fit this thing. So the first thing you should do is select the range. So you hit select range, and then you bring your mouse down, I think, and drag it. Now, how do we do it? There we go. There's the range that I selected, which is about the full range. I might have gone a little bit too far. I'll just reduce this a bit to 215. And then you say fit cycle. Whoops. Range is greater than, minimum range is greater than maximum range. Oh, what did I do? Okay, anyway, we'll fix this. And then fit cycle. There we go. And that's what it believes the best fit is now. So it's really easy to use this, and then you can go edit, examine voltage slippages. Now you get this graph. So you can see that this cell is actually pretty much irreversible capacity of the positive and negative are pretty much exactly the same, right? And you can export this data if you want, and so forth. Okay, questions?
When you selected that range, I missed why you specifically selected that range and not, all the way down to the full cell. Oh, so it's just matching it to the green line. Okay.
Yeah, I don't want to go past the end of this, and I don't want to go into this region where this DVDQ goes shooting up to the moon. Right, so I could go a little lower. This is 47. I could probably go down to 20. And fit. Yeah, so it didn't make really any difference at all. And then you can advance to another cycle. Let's go to cycle 12. So now we're on cycle 12. Not much has happened in the first 12 cycles, obviously, for a good lithium-ion cell, but there are some minor differences, and you can fit this cycle, and it'll do that, and there you go. So this program is really very useful to try to figure out what's happening in lithium-ion cells as they test over time. And I'm going to show you some case studies now where this program was used to figure out what was going on. So when I send you the program, I'm not sure how easy this is going to be because it's an exe file, so your email servers will reject it. So I will rename it as a txt file, and probably a lot of your emails servers will reject it. So then what I'll do is I'll ask Jesse to set up a place where you can go and get it, because we send this program to people all over the world, and they just go to this place where they can download the file. I'll also send you a user's manual, because a user's manual is important to understand what's going on. And I'll also send you in your homework reference curves and testing data for you to fit and understand. Okay, any more questions about this before I leave the program?
I have a question.
Yep.
So there is slippage for negative and slippage for positive. Is it possible to just have one slippage adjustment that's like relative to maybe one of the electrodes instead?
Yeah, this is really, it's the relative slippage that matters. So why do we have two of them? We have two of them because we define the zero of capacity to be when the full cell is at end of discharge. And if you only had one slippage or relative slippage, you wouldn't know how to position the curves relative to this endpoint here. So it's really the fact that we define end of discharge to be zero, that means that we need two slippages to be able to get whatever we want. But in the end, as Aaron mentions, when you look at this graph, it's really the slippage between, the difference between the end of the blue curve and the top of the red curve. The red curve slips over to the right, which we're going to see happen in case studies. That's what we want. That's due to the inventory loss on the negative side.
That makes sense, thanks.
Okay, so anyway, let's get out of here. Aaron, it's funny because when I read Honkura's paper, I couldn't understand why he had two slippages. Just like you asked the question, I emailed him and said, why do you have these two slippages? Isn't it only the relative slippage that matters? And he explained that if you fix the full cell just at zero, then you need both. And he turned out to be right. So I sent him an email saying, thank you very much. You really cleared that up for me. Okay, so I'm going to get rid of this. Yes. And I'm going to share the PowerPoint again. happening here? What do you guys see at the moment? Okay, I think you should see the PowerPoint now.
Yep.
Okay, great. Okay, so now we're going to do some case studies. Yeah, so I showed you this stuff. Yeah, when you export data, you get all these columns, you can make nice graphs. And now let's look at some case studies. Okay, so these are some cells that we've seen before when we were talking about SEI growth, right? So these cells were brand new in 2022. And then another group was made in 2006 and another group made in 2012. And at the time we had this data, we were also given brand new cells. And they have exactly the same chemistry. And the cycling is at low rate. And what's the reason for capacity loss? So we said, when we were talking about SEI, that these green curves follow the t to the 1/2 law, which is due to the parabolic growth law on the SEI. So if that's the case, what we should learn is that all capacity loss here should be explainable by lithium inventory loss at the negative side. So let's find out. Oh yeah, this is actually kind of cool. This is kind of an aside here. You know, the cells that have cycled for a very long time, so let's figure out who's who. Yeah, group 4, those are the ones that have cycled out for 11 years. What's happening? Can I go down? Group 4 are the circles. So if you take a look at the Coulombic efficiency of the circles and the squares, Group 3 and Group 4 are the cells that are the oldest. Their Coulombic efficiency in cycles at 40 degrees C at C over 20 is somewhere between 0.9998 and 0.9999. So this shows you how good lithium-ion cells become after a long period of time. Once the SEIs get relatively thick, they become incredibly good. Okay, that's an aside. Yeah. So then we took and we did DVDQ analysis for fresh cells, tested for 2 years, tested for 8 years, tested for 12 years, and actually implanted in a biomedical device inside human beings. These are neurostimulator cells that power neurostimulators, implanted in a human for 8 years and then taken out and studied. You know, so the fits, we're showing here that the fits are decent, but these don't really tell you very much. What you really want to do is look at the voltage versus capacity curves. So we'll do that. So here we are. So at the bottom are the fresh cells. So you see the positive electrode voltage versus lithium, voltage versus capacity. And the black is the full cell and the red is the negative. So there's a little bit of slippage between the two at the beginning. So if you test for 2 years, look how much inventory loss you ended up getting. Tested for 8 years, gets a little worse. Tested for 12 years, becomes even worse. And interesting, the cell that was implanted for 8 years is not as bad as a cell that was tested continuously for 8 years, and that's because when it's in the human, it's not undergoing. It's quite a rigorous testing. All right, so then what you want to do is you want to look at the active masses of the electrodes and compare the amount of inventory that loss that you got. So the difference between this and this is the inventory loss that took place over 12 years, and compare that to the capacity loss in the cell. So here's an example of the change of active mass of the negative electrode in these cells as a function of their age. So this is a very blown up scale, right? So after 2 years, virtually no change in negative electrode active mass. After 8 years, no change. Even for implanted cells, there's one outlier up here. And then after 12 years, maybe there's a small change in negative electrode active mass, possibly. And when you do the positive electrode active mass, you learn in these cells, which are LCO, big monocrystalline blocks of LCO, that there's no positive electrode active mass loss. These cells are only charged to 4.05 volts, so don't expect a big problem. So this tells you that to improve these cells, you don't have to work on making your electrodes better. The electrodes are fine, they're not losing active mass. It's all about electrolyte electrode reactions. And when you plot the slippage in percent, so this is inventory loss versus the capacity fade, measured capacity fade, the lines, the data falls pretty closely on a line of slope 1. So the best fit line has a slope of almost 1, right? So you learn when you do this work that the problem in these cells is the electrolyte. You have to improve the electrolyte through better additives, or maybe you need coatings on the electrode materials, but your electrode design is fine. You have enough conducting carbon in there, it's been calendared properly, you're not losing active mass. So we did this work in collaboration with Medtronic, who's the world's largest producer of implantable biomedical devices. And it was really quite nice because they supplied all these cells at the same time. You know, they had started cells back in 2002 up till 2014. They had 12-year-old cells that they sent to us, fresh cells, and other ones that were tested all at one time. So we were fortunate to be able to do all this work in a few months on these very, very old cells. It was quite cool. Any questions about this before I go on to the next case study?
On the previous slide, it looked like there was a negative electrode mass that was increasing in some cells. Is there a physical explanation for why that happens?
This one here?
Yeah, or even some of the other ones that are hovering around 1.
Well, there's error bars, right? This one is way outside. Like, I don't believe that this could ever happen. So maybe what happened was, you know, where did we get the original active mass from? We got it from a spreadsheet that Medtronic provided on the cell build, and maybe that was written down wrong. I don't know. So anyway, that I don't hold a lot of stock in this, just because it's impossible.
Okay, thank you. Yeah.
Okay, so here's another case study. So this is from Jesse's famous paper, and these are some cells that cycled up to 1,000 times over a period of 3, 6, 9, or 12 months. So we have cells by the colors. You can see the 200 cycle cells are black, the 400 cycle cells are red, 700 cycle cells are blue, and the 12-month cells are green. So the cells were taken off and they were cycled slowly so we could measure high resolution data and do DVDQ fitting. So the fitting is shown here for DVDQ versus Q. And then Jesse plotted also the DQDV versus V fits. So if you can fit both of these, you can be confident that your fits are great, right? And then the fitting parameters came out. So instead of giving positive electrode active mass, she calculated the capacity of the positive electrode. So you can see it was absolutely constant during the testing. And then she calculated the capacity of the negative electrode. And you can see that it was pretty constant throughout the testing. There was this jump up at the beginning. Often we see, you know, a little bit of impedance decrease in the early cycles, which maybe is responsible for this. But basically the active mass is not changing at all in these cells during this 1 year of testing. But the inventory loss is increasing. So you go from 0 to about 9. And if you look at the capacity loss, you go from 228 down to about 218. So you lose about 8 or 9 milliamp hours, and it matches inventory loss. So in these cells, again, everything is about lithium inventory loss leading to capacity fade. Now these cells have single crystal positive electrode material, where you don't expect to see a lot of cracking, micro cracking the positive. So you don't expect to see a lot of positive electrode mass loss. The lithium cobalt oxide cells we talked about earlier, the first case study, that's also big single blocks of lithium cobalt oxide. Again, don't expect to see a lot of positive electrode mass loss. So I don't want you to think that you don't ever see active mass loss, because you do in certain cases. So here's a study from Roby. I just won't go through all the details, but in this case, cells have been cycling over various depth of discharge ranges for 2.5 years. And in these cells, the positive electrode material are spherical secondary particles made up of very, very many small primary particles. And those type of electrode particles can fracture. And you can see that during the testing, you get positive electrode mass loss. You also get inventory loss, and all of this has been deduced from the DVDQ analysis fitting of quite a number of cells every 500 hours, every whatever this is, every 2,000 or 3,000 hours along the way. So you can learn a lot about what's happening in cells with DVDQ analysis, and it's a very, very valuable and powerful technique. So it's an extremely useful tool. For cells that have features in the positive and negative electrode potential capacity curves, the software eliminates the need for reference electrodes. So you can always measure the voltage of the positive versus lithium or the negative versus lithium. If you slide into your cell a small piece of lithium that you can use as a reference electrode. But that means the cell is not a real cell, because where do you put that lithium? Do you put it in the jelly roll, or do you put it outside the jelly roll in the electrolyte? If you put it outside of the jelly roll in the electrolyte, you'll learn that it measures voltages that don't make any sense, because there's large electrolyte concentration gradients that appear in the region of the cell near the anode overhang, and that leads to faulty voltages. If you put the lithium in the jelly roll, a small strip of lithium, then you have to disturb the jelly roll to put it in there, and then you don't have a real cell anymore. So I hate reference electrodes. I hate them. I think they're terrible. If you want to have cells that last many, many years that you can do science on, you will never do it with a reference electrode inside. Never. So DVDQ analysis is your way around that. Obviously, LFP and LTO are problematic because their voltage capacity curves are completely flat. There's no features. So these are problematic to use for DVDQ analysis. The software that I'm sending to you can treat blended electrodes, and we've used it successfully on LMO, NMC blended positive electrodes. So you can tell the program, look, it has a positive electrode made up of LMO, and give a reference curve for that, and NMC, and give a reference curve for that. And it will mix them together in some fraction, which you say, like 30% LMO and 70% NMC, and make you a composite voltage curve, what the voltage curve of the two would look like, and use that as the reference curve. And Alex Luley has used the program on blended negatives of silicon and graphite before. So it can do blended electrodes, it's kind of nice. And we've used this to reverse engineer cells from quite a few cell makers. For example, LG Chem's first Chevy Volt cell, which is treated down here in the supplementary information that we're not going to do. We reverse engineered that cell using DVDQ analysis, which was kind of useful at the time. We have a big library of reference curves for most common electrode materials, you know, so if you want NMC 532 or 811 or 622, artificial graphite, natural graphite, different kinds of silicon, we have a reference curve library that's very useful so that you don't actually have to go out and make your own half cells. And most importantly, you know, if you're trying to make cells that last forever and don't fail, you need to understand why they're failing and then focus on those problems. And DVDQ analysis can help point you to the failure mechanisms. So it's really very important and very useful. And I hope you enjoy using it when you get the chance. Okay, so we have a few minutes left, so there may be some questions. Let's go through them if there are.
Jeff?
Yeah.
If you have a cell that's, you know, say it's balanced to 4.7 volts, but you're only cycling it to, you know, 4.2 or some very, like some relatively low voltage, wouldn't that introduce some errors in your fit, or no?
No, it's no problem, because you're going to give it reference curves that might extend all the way to 4.7 for the positive, and the graphite might go, you know, all the way to stage 1. But in the cell, you're only going to be running to say 4.1, and that means the graphite's only going to be going out to like halfway. It's no problem. The software can deal with it. You just have to slide the slider bars around and match up what you've got. It doesn't care whether you have the cell running over its full capacity or not. It's no problem.
Hey Jeff, the DVDQ analysis is it mostly used to get an idea of the active material loss and inventory loss, or there's other things you can extract from this analysis?
Well, in principle, you could learn about, imagine you had a mixed silicon graphite negative. You could say, you know, we start with 10 weight% silicon, and after 100 cycles, how much of the silicon is active anymore, right? That would come out. So in a situation where you have large volume change materials where there's a lot of active mass loss happening, you can help distinguish, you know, what part of the electrode is failing. But yes, generally the things you can get are the active masses and the inventory loss. That's all you can get. But you know, what else happens in cells, right? There's impedance growth, there's electrolyte dryout, there's lithium plating, you know, all those things that happen as well. And DVDQ analysis can't tell you, but it can tell you if there's lithium plating, well, then there's inventory loss, and you see that big time. Impedance growth, You can measure that by other methods.
Hey Jeff, would you be able to analyze electrode materials that change in their voltage curve over as it ages? So I'm thinking something like lithium rich.
Yeah, this is where the program fails. If you have materials whose voltage curve changes with cycling, what you have to do then is create a whole set of reference curves for them at the different cycle counts, you know. So Ron was working on recently full pouch cells with lithium rich materials, and depending on the upper cutoff voltage selected, the voltage curves change with cycle count and time differently. So you would have to create unimaginable complicated set of reference curves to select from. It's just impossible. So the software really does not work well when you have electrode materials whose voltage versus capacity curve changes with cycle count. Okay, so as a counterexample though, you know, if you have a mixed silicon graphite negative, its voltage versus capacity curve will change over cycle count just because the active fraction of silicon will decrease. But the portion of silicon that's still active will still have the same voltage capacity that of typical silicon.
Kind of following up on that, is it possible to just have one reference electrode as the fresh and one reference electrode as the same, like kind of like a blended electrode, but one of them is fresh, one of them is at the end of life, and then have some sort of proportion to it?
Not in the software.
Oh, okay.
You'd have to rewrite a section of the software to deal with that. That's not in there.
Thanks.
Okay, so anyway, that's the end of this. So next week we'll start on aqueous lithium-ion cells. I'll give the first part of that, then Michael will take over, and then Chong-Yin will take over. I think it'll probably take us, could take us most of the week to get through it. Not sure. Anyway, Mark Overvac is coming on March 15, and maybe on part of the 17th to talk about silicon and other alloy negative electrodes. And then I'll do some work on redox flow batteries. And then finally, we'll get into fuel cells after that. All right. End of class. See ya.